This is How to Math with Dr. Ian Lundholm. In today's episode, the ratio and root tests. Okay, today should be pretty quick. We've got two major tests to talk about. Again, we're going to be testing infinite series and determining whether they converge or diverge. The first test is the ratio test. This is again, it's a ratio of sequence terms, but kind of the guiding infinite series that I'd like you to have in mind right now is the geometric series, because what we're looking at in this ratio is a ratio between successive terms in the series. We're looking at the ratio of an plus 1 to an. Remember that in a geometric series, that ratio is constant. And when that when that constant ratio r is less than 1, that's when a geometric series converges. So the ratio test very much takes its inspiration from a geometric series. And if the limit of the ratio of successive terms approaches some limit less than 1, then the overall limit converges. That's part A here. So if it eventually behaves like a convergent geometric series, then it would converge. For part B, if that ratio eventually tends to some number that's greater than 1, or if that limit equals infinity or goes to infinity, infinity is greater than 1 last time I checked. So, that would be the divergence case. And we have this third case of inconclusivity, where if that limiting value is 1, it's inconclusive because actually it could converge or diverge, as we'll see in just a second. There are examples of both. First, we'll look at how we would prove the cases for convergence and divergence. And do know that the ratio test is really only paying attention to the tail end behavior in the series, because that is what is important. The first few terms in a series doesn't necessarily affect the overall convergence or divergence. The first several, 100 million terms could be really, really big, but if the last, infinitely many terms settle down, then the thing could still converge. Let's take a look for part A. This is the convergent case. Since we know that geometric series with a ratio of less than 1 converge, what we can do is use that knowledge and combine it with our knowledge of, the definition of finding the limit of an infinite series. And we get this part down here. Basically what this says is if we know that, let's go back to the test. If we know that this specifically is true, I'm putting a box around that, but let's clear pen markings. Okay. I want to box all of this. There we go. If we know that the successive terms, an and an plus 1, if that ratio approaches a number less than 1, and we're calling that ratio, that number that is less than 1, L, we're starting off with this information as given. That gives us this piece down here in blue by the definition of what that limit is, according to the epsilon n definition that we looked at a few sections ago. So we have this limit, and basically what we're saying is that we're able to put an epsilon bound around this eventual limiting value such that after you get past some point in the series, we'll call it big N, then all of the terms in this, series are within that epsilon bound. And basically what we can do is squeeze a convergent geometric series on top of that. So yeah, this is what it looks like to squeeze a convergent geometric series on top of, this little epsilon window around the limiting value. And that convergent geometric series on top, we know converges. So by the direct comparison test, we know that the original series converges. Cool. For part B, to show that this thing diverges, really all we'd have to say is that if this ratio is greater than 1, then we know that this thing is not settling down and the terms do not approach 0 as n goes on. So that's definitely divergent. And then here's where, if the limiting value is 1 in the ratio test, then it could go either way. This one is a convergent p-series and has a limiting value of 1 in the ratio test. And the harmonic series, we know, diverges and also has a limiting value of 1 in the ratio test. So there's two examples. They could go either way. All right, now let's take a look at some series here in example 1. Let's think about whether each of these converges or diverges. Looking at part A, we are in a war between n to the 7th power and 7 to the n power. The geometric part on bottom, the exponential part on bottom, is going to grow faster as n goes on. So that's going to win. I believe that one will behave more like a geometric series and will actually converge nicely. In part B, we have a war between two factorial expressions. I'm thinking the top of that's going to be bigger, and it'll probably diverge. And then part C, I think we're going to get an inconclusive thing there. It looks a lot like the harmonic series. We've got that extra ln of n factor on bottom, so maybe it could converge since there's more going on bottom, but yeah, we'll see. All right, so first one. This is what it looks like to take the ratio of the n plus 1th term and the nth term. Remember that when you're dividing by a fraction, you can flip and multiply. And working this down means that we find that the eventual, limit between the ratio of the successive terms is 1/7, which definitely means it will converge. Cool. And yes, that does not give us the actual sum of the series, but we know that it converges, and that's good enough in a lot of scenarios. Here we go with the n plus 1st and nth term of that factorial series. This, I don't know if you don't know what a factorial is. Let me write one real quick. It's just the product of all of the numbers below the given number that you write in front of the factorial. So n factorial is n times n minus 1 times n minus 2, all the way down until you get to 1 in the end. So these are just huge products on the top and bottoms of these fractions. But there is a lot of cancellation that goes on, and eventually you're able to find that this approaches 4 And so, indeed, the top of the fraction was bigger than the bottom of the fraction. And yeah, this thing definitely diverges. The terms don't even approach zero. Cool. And here we go back to that n times ln of n1. This is what it looks like to put it in the ratio test. We get to do some L'Hopital's rule on this. First we split it into two limits. The first one's easy enough. This one just turns into 1. But this is where we end up doing L'Hopital's rule. And after you do L'Hopital's rule, you again find pretty much the same thing and find that you get 1 in the end. So this is inconclusive. And if we wanted to figure out whether this thing converged or diverged, we'd have to use a different test. Thankfully, we have a few tests in our repertoire now, and it looks like the integral test might be something that's productive. So if we take this integral and do a little bit of u substitution, where u is ln of x, we get that as an antiderivative, and that diverges. And so that would diverge with the infinite series. So the ln of x was not big enough to make that whole thing converge. Okay. And that's it for the ratio test right now. Moving on to the root test. Here, again, we assume that we have a series of non-negative terms and that this limit either exists or diverges. We've got 3 cases, and the 3 cases look very, very, very much like the ratio test. I think that's why they're in the, come on, in the same, the same section, ratio and root test. So we've got the case where this nth root is less than 1. We've got the case where this nth root is greater than 1. And we've got the case where this nth root is 1. And again, proving why each of these works out the way that it does for convergence or divergence. Again, we can use the idea that we can kind of squeeze a convergent geometric series over top of the convergent version and use the direct comparison test to show us that the original series converges. Again, for this one, we can show that the nth term in the series does not settle down, doesn't converge to 0, and the overall series would diverge. And then again, 1 over n and 1 over n squared give you different conclusion, give you the same conclusion that the limit here in the root test would be 1, but those definitely are different types of series. One converges, one diverges. All right, we're going to take a look at some examples of new types of series that we're now able to determine whether they converge or diverge. And for part A, this one looks really, really similar to one that we just looked at for the ratio test. So yes, you could use the ratio test on that one. This one you might also be able to use the ratio test on this one, but the root test is going to be nice because we end up taking an nth root here, and we have an n in the exponent. And so those things will cancel out, and it's going to be really straightforward. Again, we have an n in the exponent over here, so whenever you see an n in the exponent, think, oh, maybe the root test might be helpful here. Okay, so here's the first one. We take the nth root of the nth term and look at the limit as n approaches infinity. Here we are just applying that root to the exponents. And yes, we see that this converges to 1/3 as a limit. And therefore, we've got, convergence. Cool. For the next one, we've taken the nth root of this nth power, and a lot cancels out, and we see that this limit's just going to go to 2/5. So, converges. Great. And the last one, here again, we have basically, divide the exponent by n, applying the nth root. And this approaches 0 because ln of n continues to grow, and this one goes to 1. So overall, that fraction goes to 0, and so that one will converge. We had 3 convergent series in a row. Cool. All right, example 3 is an odd one, but it shows you a case where you might want to use the ratio test, but the ratio test will let you down, and the root test comes in to save the day. So yeah, we have the series defined in a piecewise fashion, such that the odd terms look like this and the even terms look like that. Basically what we have is kind of 2 subsequences for the terms. And we're trying to determine whether the overall sum converges. Cool. So trying to apply the ratio test, there would be 2 forms of the ratio depending on whether n is odd or even. And that gets confusing, right? You're still taking the same ratio of the nth term and nth plus 1 term, but these look completely different depending on whether n is even or odd. And that's totally because we define this in a piecewise fashion. But these 2 things would give you a different limit. If you are taking the limit as n goes to infinity of each one of these, this one would go to 0. This one would go to infinity. So that's a problem for the ratio test. And so really, if you're taking all of them together and you're letting n go to infinity, the limiting part of this would oscillate between 0 and numbers that are growing unboundedly towards infinity. And this limit fails to exist in a fairly extreme fashion. But if we use the root test on this one very handily, this numerator in this fraction goes to 1 as n approaches infinity, and we get the same limiting value, so we're able to conclude that this series converges using the root test. So there, the root test was handy for that particular, piecewise defined thing. It's not always going to be that way. Sometimes the ratio test could be more convenient than the root test. Just kind of depends on whatever series you're starting off with. But hopefully that was a quick and somewhat clear introduction to the 2 tests, the ratio test and the root test. And those are good for infinite series that kind of behave like a geometric series over time. Here is a meme for you all. And I will say, this has been How to Math with Dr. Ian Lundholm. Remember, you have online homework to do, and now you're ready for it. I'll see you in the next one.